I selected the thing here on the red display, so we'll see. It's not. It's not a Michelangelo. I need to use the mic. Okay. So hello. Oh wow, this is loud. Speaker, obviously. My name is Marcel. I'm giving the next talk on software architecture. So I just can second almost everything that my previous speaker said. Yeah, and so this is kind of going beyond that. So when you start looking at architecture, and you want to try to express it more directly, because we have these architectural elements, and we can't really deal with them. They're always indirect. And somebody mentioned, we don't have any tools to check what the architecture still works. This is sort of about that. So let's get going. This is an overview of the talk. I'm going to first, and this is going to be a very bullet point heavy talk, so bad talk. First, I'm going to talk a little bit about the problem, Brooks paradox, right? Brooks, the mythical man-month, no silver bullets, architectural mismatch, which is related to the problem of that we have two grammars. And obviously, say what that means. I'm going to talk a little bit about what I think the solution should be, and that involves a language I've been working on since forever, which I call Objective-Smalltalk, and then some details about that language and progress since I talked about it years ago, and it's actually progressed. Not much, but a little bit. And there's elements like hierarchical messaging, polymorphic pipes, storage combinators, constraint connectors, and what I'm working on right now, configurations. And so let's get going. The first part is the problem, right? So what is the problem? Brooks paradox. So we just have too much code, in my opinion. This is a little graphical representation of that. And so at Xerox PARC in the 70s, they kind of built personal computing. So they had word processing development, they had email, they had a proto-internet. And it was about 20,000 lines of code on the Alto. And if you look at the Hacker News Y Combinator research stuff, they're restoring those Altos right now, that 2.5 megabyte disk pack, 128K of memory. The slightly larger rectangle is the source code representation for Windows and Office. Actually just Office. It's 400 million lines of code versus 20,000. And I've actually, since I work for Microsoft these days, I have the source code on my laptop, and it's 25 gigabytes compressed. That's just Office for Mac. There is no way any living person can understand that code. It's just not possible. Now, of course, Office does more, right? So let's assume it's 100 times better, does 100 times more. I think that's, I'm not really sure, how much better you can make, word processing and basic Office tasks, but I think 100 times is generous. So what happens? Well, that's the box. That little rectangle now would be 100 times more than what PARC had. Still a big gap. So we don't know what 99.5% of our code is really doing. That's a problem, I think. And my personal experience is kind of like that too. Whereas Brooks said, there are no order of magnitude improvements. That was no silver bullet, right? There are no order of magnitude improvements left in software. It's just hard. And this says, well, something's wrong, because there's a lot of orders of magnitude here that we don't know what's going on. But his argument is extremely good, that we don't have that. But in my personal experience, actually a lot of the code I write is fairly trivial. It's just, connecting stuff. I work on window list and that to do, and it's just, there is some data over there, please put it over here. And I put it on the screen, and somebody made a change, you reflect it all back. I don't see that as deeply intellectual, fundamental complexity. It's really boring stuff. So why is it so hard? So one of the reasons that I'm aware of is this thing called architectural mismatch. So one of the solutions that Brooke came up with, well, or thought would solve the whole thing, was reuse. Obviously, right? We write it once and then reuse it, and it's worked pretty much. I mean, we can write. We now take a lot of reuse for granted. We have stuff on GitHub. We download it. We use Cocoa UI kit. We could never do this. We could never write the apps from scratch that we do today. We reuse a lot. But there is a problem with that. It's that the components often have different assumptions about what the architecture of the entire system should be, and therefore they don't match. And so you always have this glue code running around that needs to adapt them to each other. And there's some studies that actually this grows not linearly but super linearly, probably quadratically. And oh, wait a second, we got more stuff, and that curve goes up. Maybe that's. And actually, 20,000 lines of code, 0x Park, 400 million lines of code Office, well, that's n squared. Probably just a coincidence, but maybe not entirely. And especially when so the first article was in, I don't remember, it was 90s, I think, and then 10 years later, they had another one, nothing's changed, it's all just as bad as it's always been. And then just recently, there was another very good paper about the specifics of architectural mismatch in graphical applications. And there it's even worse, because the architecture of graphical applications fundamentally does not match the architecture of the programming languages we are required to program them in, right? Because all our programming languages essentially are call return based. So you call a method, you call a function, it does something and it returns. That's what we have. Well, my graphical apps aren't like that. I'm not sure about yours. They stick around. They usually have some kind of homeostasis going on. I don't call them, they give me a computation and then return. So there is a very fundamental architectural mismatch going on right there. And another problem that's related to that is that, okay, we've realized this now, and so we use an architecture that's something different, data flow or reactive, what have you, but then we have two grammars. And actually, even object-oriented architectures are like that. We have the grammar of the source code that we write this in, which is called return, and then we have the grammar that's the actual runtime architecture, right? And these two don't match, right? So when I have an NSView hierarchy, for example, or UI view hierarchy, the actual grammar that's embodied in that view hierarchy, there's grammar there of some sorts of, these can be composed in these different ways, is not at all visible in the source code. Because the source code just said, well, here's a function call, here's a message send, and it does something. And you have to keep that in your head. And that conflict also means that there is a cost to having to using a domain-appropriate architecture, because it's going to be very different from the architecture that you can express in the code. So you're moved away from actually trying to do a correct architecture. And I first really noticed this when looking at frameworks. So yeah, framework-oriented programming, I'm a big fan. And so one of the first type of framework we had was white box frameworks, where we just do subclassing, right? Then we had black box frameworks, where we had sort of components that we arranged. And it turns out that black box frameworks are equivalent to a domain-specific language. And actually some of the, when you have a more sophisticated black box framework, often it comes with a domain-specific language. And in a way, Interface Builder, for example, is a visual domain-specific language for UI components and for hooking them up, right? We say this talks to that guy and that one talks to that guy, and they're in this hierarchy together. But it's only visual. It's good, it's nice that it's visual for the visual parts, but it's certainly not really useful that all the connection parts are also visual. And just as an illustration, I would like to write this, right? Maybe you've seen this before. This is the architecture of Wunderlist and of To-Do. And we have a UI, and we have a memory model, and we keep them in sync. That's the equals pipe equals means keep those two in sync. We have a memory model. We initialize it from our persistence. After that, we keep the persistence up to date with our memory model. And since this is a web-based app, we have a backend, and we want to keep that in sync with the memory model. Done, right? That should be my app, and I should be able to decompose from this. I can't. That sucks. So the solution. One is I like to remove the glue as much as I can, and that means I actually have to focus on it because I have to make it a first-class entity. So I can encapsulate different kinds of glue that are appropriate for a specific application, and I want to express it directly. I want to express what my architecture directly. So as an example, that's a Unix pipe, and that's essentially, I mean, the perfect embodiment of that, right? Because you have components that are fixed, and you can combine them in any way you want, because there's a very flexible interface between them, which is the pipe. But you never write any glue code. Your glue code is the pipe symbol, right? Because it's completely appropriate to that interconnect. And in fact, the predecessor of Unix had, Multics had a more procedural interface to this. So there you have to say, well, set up the standard output of this component to point here, set up, and that's just not as useful. And just like we have to do when we are setting up our components. So it'd be not much nicer if you just say, yeah, here, this is the layout that I want. But the problem, of course, is that we can use, I mean, Unix would be nice, but of course we can't use it because it's not appropriate for our domain. So it'd be nice if you can abstract or redefine our connectors. And that means directly writing that second grammar, eliminating that glue, and that does actually mean that you need syntax, so you need a language to do that. But at the same time, when you have that perspective on the code and you have seen that second grammar expressed directly, it actually also helps you write if you don't have it available. So we've been using the architectural insights that come from this in Wunderlist and To-Do since 2014, and it actually, we've actually maintained that architecture. We have refined it, but we never had to throw it away. It's just gotten better over time. For example, a colleague just recently did a new feature and said, yeah, it took me 20 minutes. That type of feature used to take 2 weeks. And it's not a unique case. It just keeps getting. So, yes, you can do this on Objective-C, probably also in Swift, although Swift is a little bit more difficult. It has an advantage. It has a more flexible syntax in some cases. It's more difficult because the compiler is very strict, and so when you express an architecture in a different architecture, you need some wiggle room that the Swift compiler doesn't like to give. So you have to be very creative. But I've seen some very interesting approaches to making that happen. So in Objective-Smalltalk, we have wait a second, that's in there. Well, first Objective-Smalltalk, right? So what is it? Well, it's the actual Objective-C without the C, because that's just Smalltalk, and then we add architecture stuff to it. Yeah. So, in Smalltalk or in Objective-C or in Swift, you mostly have a single mechanism. Here you have a hierarchy of these interconnection mechanisms. And then you can start playing with them. Higher order messaging, yes. So higher order messaging, I don't know if you're familiar with it. That just means you have a message that takes another message as an argument for a message send. I actually started with it because, well, Objective-C at the time didn't have blocks, and I hate writing loops, and so I just added collect and do. Surprisingly, to me at least, the most popular higher order message in our code base is if responds, because it just handles that delegate pattern. Alright, so if delegate responds to selected blah, then send the message. And who spotted the error?
Localized statements?
Yeah, exactly. Right. You write it twice, and yeah, that happened to us because we happen to be human. Yeah, with a higher order message, the if response just takes the rest of the message as an argument, and voila, you just write it. And also, you don't have to parse this, right? It's obvious what it does. Whereas the other thing, is it really doing what I think it is? And it turns out that higher order messaging just eliminates a whole lot of these patterns. There's a talk by a guy called Sam Adams from IBM called Big Boop. Yes. From Smalltalk Industry Council, and actually he came up, I think they came up with that independently, and he really talks about how the amazing number of patterns of glue code, and specifically calls out glue code, you can eliminate using that type of system, which you call adverbs, right? Because normal messages are verbs, these are adverbs that control how the verbs get sent. This means, well, optionally, collect means send it to all these objects and return a result. Async, right? Send it asynchronously. Future, send it asynchronously and give me a future back because I want a result. And so on. So at one point, I actually coded the targeted the first responder system as a single higher order message. You get rid of our architecture that way. And so a quick demo. So wow, that's my little Objective-Smalltalk shell. Hello. Okay, you get the idea. Let's see. There's one more. So that's one difference with higher messages and typical block-based approaches is that because the message send is much simpler, it can just iterate over any combination of the arguments. And of course, actually, Philippe Mugano did F-script, and he actually did sort of an APL operator type where you start doing cross products and stuff. That gets really cool very quickly. I don't understand half of it. This is sort of my level, and I find it very useful again in actual code. So back to the demo. I have 2 slides. So next, polymorphic pipes. As you might have noticed, I'm a big fan of the pipe and filter pattern. And a long time ago, I wondered what would pipes and filters and OO be if you put them together. And it turns out, really to get the benefits of the pipe and filter architectural style, you really don't need that much. You really just need a uniform interface for input and output. And so you don't really need multiple processes. You don't need these active components. That actually gets rid of the pipes. The pipe just becomes a message send. And because it's objects, they can react to specific types of objects that are sent, whereas Unix pipes and most of the sort of data flow mechanisms I have seen so far don't do that. They're monomorphic, which means, for example, this is very useful for, well, for example, for printing something to standard out, because every object can have a specific, well, I want to be printed on this debug, on a debug stream. And if it doesn't have, it can fall back automatically to just the normal description. And also for serialization, XML, JSON, what have you. Yeah, again, you can disassemble the object graphs and reassemble them. And also it's really good for asynchronous code because data flow code does not care about control flow because, well, it's data flow. And we started using that in the to-do client last summer for our new backend that talks to Exchange. And it turns out that now we have this little graph, which is essentially our SDK. And what's different about this from other, boxes and arrays graphs you see with architectures is that these actually have a very simple and specified meaning, because every box is just a filter, and every arrow is just this in-process pipe connection. So this graph has actually been produced manually, but you could in theory just produce it straight from the filters at runtime. And ideally, actually, since this is done in GraphWiz, it would be really nice if you would actually just take the GraphWiz and use that as your pipe specification. And I know there's at least one data flow language that did that, but we haven't come around it. So, yeah. Actually, most of this is the error handling, as usual. The main part is here. With our services is our abstract application, and that just talks to the backend via queue, where you put in requests, and there's a list syncer. You have to do pagination, and we go to we get lists back, and then we have to convert those to tasks, and so on and so forth. Again, it's suddenly gotten very simple, the whole thing very testable. Even though it looks like a lot, but it looks like a lot because it's actually at a very fine level of detail, which usually architecture diagrams are not. And let's see a quick demo. I had this just a short time ago. Oh, there it is. So, yeah, this says, well, you have a standard in, you have stuff coming in, and then you have a block. We get the string value of whatever came in, we take uppercase and we put it to standard out, and so let's run that. Surprise, something worked. Woo! Next, polymorphic identifiers and storage bindings. That's actually been probably the biggest win so far, because storage is always kind of, well, there's stuff and it kind of works. This is a framework for making it somewhat well-defined, what you're doing. So the idea is that in most languages, we abstract over the procedural parts. So we have Objective-C, Smalltalk, Swift as well, most object-oriented languages. Once you're inside the object, you talk about storage itself. It's monomorphic. There is no way to compose these things, even if you have, in the new Swift proposals, for example, specific methods you can call. You can only do that on a per property basis. You can't abstract over entire classes. of these. And also, time has moved on, right? We have the internet, we have direct file access. And so the idea was, well, all identifiers in that programming language are URLs. You have scheme handlers that you define yourself, and you can compose them. So, for example, if I want to just read a file, well, I say var :foo is equal to file::foo.txt, and that's it. If I want to do it the other way around, I just put the file::foo.txt on the other side. I can make an adapter and then SQLite reads the database, and it's all the same. And I can the names are obviously replaceable, so I can call SQLite just mydb or whatever, and then I can substitute them, and I can compose them. And you also have universal first-class references for things like when you need to have a UI element that is supposed to be parameterized with something that it modifies. In CocoaLand we need either key value coding, we need to do it ourselves. Here you can just have a reference and give it a reference, and you can say set value, there you go. And you can do that with any type of reference. So, since the scheme handlers have a uniform interface, which is essentially just a REST interface, so get, put, post, that sort of thing, you can compose them. They all have the same interface. And therefore you have these sort of a basic structure of, you have providers that have raw data, file, HTTP, your internal variables, what have you, databases. And then you have combinators that just act as filters. And so, for example, you can transform the identifier that comes in. You can transform the data that comes out. You can add new entities. You can switch. So if you have different data sources, you can just put a generic switch in front of them and say, well, this goes into the keychain. This goes into the JSON store. And once you have a couple of these combinations, you can just start playing with them. And you can also put consumers on top. So for example, HTTP servers or Fuse file system, or of course your own stuff. And so when you have, for example, the HTTP storage combinator, it actually is a combination. It's actually already composed of, well, there's a cache in memory, there's a MIME mapper that automatically does a translation based on MIME type, and you put a file cache in front. But you can actually also make it more complex, right? You can do a file cache and an memcache, and it is really just plugging these things together. And this is what actually how we use the storage combinators, at least that, well, I'm not sure it's completely current, in to do. So we have a disk store, we have a filter that does JSON to and from. The Microsoft manager does a keychain, then there's a switcher which says, well, there's user data, well, put it there, and if it's other data, put it in the JSON store. Then we have a cache, which is also a generic component. Well, get it from the memory. If it's in the memory, fine. If it's not, well, go to the other one. And so on and so forth. Then we have a bunch of filters that actually sometimes do a little bit of post-processing, and sometimes actually you can add complete new entities that are synthesized from what we have. And the point being that the UI has a simple interface, and the interface doesn't change, and we just keep plugging it in. So we now have essentially one table view that just knows how to talk to a storage system like this. There's a bit of adaptation, not still necessary, but not a lot, and that's also flexibly handled. We just removed, I think, by having that and then we had this for a while, and then we actually adapted the UI to actually take advantage of it. I think we removed 20,000 lines of code. And that was one of the crucial bits where, again, my colleague said, well, this took me 20 minutes to implement. I thought it was going to take a week or two. Polymorphic constraint connectors. This is the really cool stuff, but it's not done yet, obviously, because that would be cool, right? So, you saw little architecture overview I had over at the beginning. And actually the first part, that's MVC, right? So this is, I'm just describing the whole pattern, the whole architecture, just in a line of code. Of course, it doesn't automatically do the implementation. You actually still would have to implement it. Well, then we had, some persistence, and wow, that's core data, or something like it. And then we talk to the backend, right? And that's, a whole lot of frameworks. And again, of course, all the connector in each case is different. So this is what they're polymorphic connectors. But I should still be able to actually do this, write this down, and then break it down. And that's kind of where we can actually go. So let's take the universal example, which is a temperature converter. And so the first part is the UI. And so we have a Celsius text field. And we say the integer value of that should be my Celsius local variable, instance variable. Same for Fahrenheit, same for Kelvin. And I should initialize that from the default database, and I should keep the default database in sync with what I have. And instead of a backend, we have a local model that just does its own constraint handling. And this is just a couple of formulas to make sure the temperatures will match up. And of course, you can't actually write that, except that you can. So I hope this is not too small. This is the actual code. Minus the persistence at this point. And the demo grounds are friendly. Yeah. So if you actually had to implement that using sort of normal MVC patterns, it would be a lot of code. And each time you make a change, and that's, there was a question about that, what happens when you make changes? Well, oftentimes, because of the communication patterns, because of the glue code, you have to go everywhere and say, I need another hook here to say, something changed, and now I need to make, actually change the architecture to be more abstract, add notifications or not, or something, right? And here it's really just linear, as we saw just a second ago. And I've done that before, so I just added the lines of code and you just add stuff when you add requirements, because all that interconnectedness is handled by the constraint system. And this is now implemented by having the constraints resolved by the delta blue constraint solver. The idea, of course, is that the constraint, so that's a specific instance of a constraint connector. And of course, the idea is that you can substitute your own. So you can say, well, if I have backend HTTP communication, that's not going to be my local delta blue solver. That's going to be something I have to custom write. But actually, that's also fairly simple, because it turns out that a data flow constraint can be expressed. There's two variants. You can have a push constraint. That's easy. You need to target it. When you change, you just push data to it. Or you have a notification mechanism if you have a pull constraint, when you don't want to have the other directionality. And that's actually just like MVC, real MVC, not Apple MVC. Low power. Oh my. Gotta talk quickly. So that's the constraint connectors. And so this is the last. Oh, why is it going back to this? Sorry. What? I don't know why I had that. Okay. So the last bit is configurations, and that's kind of one of the pieces that, again, I'm still working on. And as I talked the other day, it's just recently, so, you need to take a walk, and that's what I did. And I took a walk, and I noticed that actually, well, it's really close to sort of dictionary, literal syntax. And so this actually is like that, except you can specify a class. And so this is saying I have an index view with a frame, and it has a single subview that has an alpha value. right? And that is very similar to the various mechanisms that, people have. One of the ways of seeing, where is a demand is that people keep rewriting these JSON builders, right? I've seen probably at least 3, 4, 5 of them. Now everything is going to work because I can just specify my UI in JSON and then everything's going to be happy. It doesn't tend to turn out that way because you can't refactor JSON, you can't compose JSON, you can't subclass JSON. And that's the same problem you have with interface builder files. You can't subclass them, you can't really compose them very well, and you can't abstract from them. And a lot of people, in our team, we keep bouncing back and forth between, well, we should use interface builder because it has all these great features. Oh crap, interface builder sucks because you can't refactor and you don't see the code. And we just keep bouncing back and forth, and that obviously means there's a problem here to solve. And neither of the solutions are correct yet, but they both have sort of part of the correct solution. This is super simple at this point. Being sort of that type of liberal syntax, I can talk anymore. You can actually do further computation inside. So, for example, if you wanted to say, I need 10 of these, you can put a little loop in there. That's not a problem. But on the other hand, it's probably simple enough that you can actually do a UI tool with it. And also, and that's something I haven't talked about yet, is that this being a highly interpretive language, there's no problem with actually having changes to a running application, and that again makes for a very, very useful workflow when you're doing fine-tuning of user interfaces. Yep, that's pretty much it. And again, the whole thing is sort of like going back and forth from theory to practice with some linguistic development, and the theory informs the practice. The practice then gives new problems that inform the theory, and all of that, connecting that architecture to the real implementation. Ideally, I want to write Wunderlist or in a couple hundred lines of code and have it be architecturally sound. Currently, when we do that, we tend to need to use sort of rapid application development tools that then we don't